Is MTTF a measure of reliability? That's today's topic. A car manufacturer is using a pedal assembly that is made by one of its suppliers. The acceleration pedal is one sealed block that, if found faulty, is changed as a whole piece, and for the car manufacturer it represents a typical interchangeable component. Unfortunately, the electronic components within the pedal assembly were of lower reliability than it was expected, which cost the car manufacturer a significant amount of money due to warranty claims. At this point, about 4% of cars developed the failure within the first year from the sale date. The reliability of the pedal was verified, and according to the accelerated laboratory test, the MTTF, the mean time to failure, conformed to the required criteria of 8 years. As the problem was progressing, the action team decided to change the electronic parts of the pedal and the way these were positioned within the assembly to reach a newly set increased target of 10 years. The improved design was successfully tested for the new target and implemented to production. Up to this point, the team solved the problem successfully. But after about 8 months from the start of the production, the cost of the warranty claims for the pedal assembly was still on about the same level, and according to the data, the failure rate even increased to about 6% within the first 12 months. Not surprisingly, the reliability is from the beginning to the end dependent on the use of statistics, as the time for which the components are actually functioning is a typical random quantity. From the statistical point of view, the reliability in general is not very different from the other problems. There are some special approaches, but in general, there still are metrics, distributions, quantiles, estimates. But the real challenge is the engineering part. Due to a complex nature of possible failures, the reliability is not very intuitive. It is especially important to pay a close attention to cooperation and agreement between the technical problems and their possible statistical solutions. The statistics is always a supportive science, which can never substitute the technical competency. But the more advanced is the technical competency, the higher are the benefits from the use of statistics. The investigation of the problem was actually easier than one may expect. In this case, it was not necessary to review the relevancy of the laboratory tests, which is usually the most puzzling problem, but it was necessary to challenge the way the reliability itself was measured. As it was mentioned, the reliability here was expressed as a mean time to failure, which is the metric commonly used for non-repairable components. Its calculation is quite easy. You take a set of components, subject it to a test, mostly in laboratory conditions, and measure the individual times to failure. The mean time to failure is just the average of the individual times. In the real world, we usually don't have all components failed, so we need to account for those that survive till the end of experiment termination as a censored observations. Many times, we need to combine data from various sources, like our different types of laboratory tests, real condition tests, and customer application reports. And also, the time to failure can seldom be approximated by normal distribution. So the calculation of the confidence bounds of the MTTF is not as straightforward as it is, for example, in the measurement system analysis. The key for understanding the reliability is the statistical distribution associated with the time to failure. The reliability itself is defined as the probability that the component will be functional after some period of working duty. We can picture a hypothetical large group of, let's say, 1 million of pedal assemblies that all started to work at one point of time and they all were functional at that point. As the time elapses, some pedals start to fail, and the number of the functional pedals will decrease. The portion of the pedals that are still functional is equivalent to the probability that any single pedal is functional at the time. Statistically speaking, the presented reliability function is one of possible representations of the distribution function. If we estimate the reliability function, we can easily picture it as, for example, the cumulative distribution function, or as the probability density function, or the famous bathtub curve, officially known as the hazard function or the instantaneous failure rate. The shape of the distribution function reflects all the different phenomena that are able to develop into a failure. It is not unusual to see a steeper drop of reliability during the early months of operation than in the later time. I exaggerated the presented picture compared to the real situations for the sake of the presentation. We usually need to zoom into the early months region to see what is happening. If we compare the reliability curves of the pedal assembly before and after the improvement, we can clearly see significant improvement in the mean time to failure. But if we zoom into the upper left corner, we can also see a drop of reliability. Actually, at the time of 12 months from the sale date, the drop of reliability from 96 to 94.5% corresponds exactly to the observed failure rate increase from 4 to 5.5%. And this situation is likely to progress more till the end of the 24 months warranty period. This phenomenon comes from the way of design improvement. In order to increase the mean life, the designers reinforced some parts of the assembly which had the desired effect. However, at the same time, this change caused an accumulation of stress in different parts of the assembly. This newly stressed area was not that sensitive to the new load, but those few parts that failed actually failed quite early. The reason the team did not see the unfavorable effects of the improved design lies in an inappropriate definition of the reliability target. The mean life which was used here is reached at a point of time that is very distant, and that is of little interest both from the point of warranty coverage and customer expectation. The customers are likely to accept when an 8 or 10 years old car develops a failure. What we really need is a high reliability in the defined interval from the beginning of life, and the high reliability is certainly higher than the 40 or 50% at the mean lifetime. The solution must therefore begin with a redefinition of reliability target. We can do that by setting certain fixed points in time and a minimal reliability at those points. Let's say that we want to have less than 4% failure rate by the end of the warranty period. We block out a part of the reliability graph to the left and down from the defined point. The reliability curve can now be anywhere in the region, but it must not interfere with the blocked area. Here is a picture of two examples which meet the criteria marginally. Now we have set a target in such a way that the design team can use it for the optimization of the product. If the product conforms to such criteria, there will be a controlled level of failures and warranty claims, regardless of the mean time to failure. If we want to better control the failure rates also at different points of time, we can define more points or maybe a curve. Please remember that MTTF is not a good measure of reliability. The improved MTTF may or may not mean an increased reliability at the time we need it, and it is therefore only confusing people who design or test the product. In most cases, the entity F can do more damage than good. The technical, statistical, and economical approach to reliability problems can get the matter only so far. There is a level which needs to be addressed from the ethical and philosophical standpoint, and vice versa. The ethical aspects shall be accounted for in the technical and statistical solutions. Let us know what you think about it.